Hey guys, Mr. Jantzen here to take you through the 100 illustrated ways to pass the Earth science Regents. Today we're talking about numbers 51 through 60. Okay, 51. Generally with the passage of a cold front, the temperature and humidity decrease and the pressure rises. Okay, so a cold front brings cold air. That makes sense. But the humidity decreasing, what's going on here is because the air is cold, the molecules are close together. So if the molecules are close together, then you can't fit a lot of water vapor in between them. So your humidity is going to drop. So cold fronts are fast moving. They are going to force warm air up. They're going to be associated with thunderstorms. These big cumulonimbus clouds will form when that warm, moist air rises. And, you know, if we were going to see this as a Regents question, it may appear something like this, okay? The weather map below shows a cold front approaching three cities. The two isobars are labeled A and B. Which weather events will probably occur in Millsville as the cold front passes, okay? So here's Millsville here. Once again, we know the temperature is going to drop, okay? And it's going to be associated with an increase in clouds and a thunderstorm. So the choice that says that here is going to be choice A, an increase in clouds, a brief thunderstorm, and a shift in wind direction. Okay, 52. Generally, with the passage of a warm front, the temperature and humidity increase and the pressure decreases. Okay, warm front brings warm air. That's why the temperature is going up. But warm air has the molecules spread out. If the molecules are spread out, then more water vapor can get in there. Okay, so that's why you're going to have an increase in humidity. Okay, but once again, wet air is actually, okay, lighter than dry air. Okay, those H2O molecules are a little lighter than the nitrogen molecules, so moist air has a tendency to rise. So if you have, you know, water or moist air rising, then you're going to have less pressure. That's why the pressure is decreasing. Okay, so once again, you know, that warm air is kind of being moist and rising up and forming clouds, kind of associated with a little bit more prolonged precipitation, not a quick thunderstorm. Which statement best explains why the precipitation occurs at the frontal surfaces between the air masses? Okay, so once again, cold fronts move fast, warm fronts move slow. However, with a warm front, the warm moist air is going to rise when it meets cold dry air, okay? Or it's going to be choice C right there, okay? Very good. Number 53. An included front is formed when a cold front overtakes a warm front. So you have a cold front moving very quickly, like we talked about, and it basically catches up to a warm front. So behind the cold frontal boundary, you have cold air, but in front of the warm kind of front, you have cold air also. So it's almost like the cold air kind of teams up on the warm air on either side and kind of picks it up and body slams it out of there. Okay, so once again, it kind of quickly catches up to it. All right, which is kind of neat. If it was going to see the Regents question, the diagram below represents a cross-sectional view of the air masses associated with a low-pressure system. The cold frontal interface is moving faster than the warm frontal interface. What usually happens to the warm air that is between the two frontal surfaces? So where is this warm air going to go? Okay, and it's going to basically kind of be picked up and, you know, thrown out of there. Okay, the warm air is forced up over both frontal interfaces, or choice D. Okay. 54, cold fronts move the fastest. We mentioned this, okay? They're going to move in very quickly, associated with thunderstorms, and kind of move out of there, all right? As a Regents question, it's kind of straightforward. Which type of weather front moves the fastest? Cold. Has to be memorized. You have to kind of know that walking in, okay? Number 55, as air rises, it expands and cools, okay? This is called orographic uplift. So, once again, mountains can force air up, whether it's, you know, especially cool air, okay? And that's kind of weird because you're so used to warm air rising, but in this case, cool air is going to rise. When it rises, it's going to expand, cool to the dew point, and form clouds. So this is what we call the windward side of the mountain over here. And then it gets rid of all its precipitation, all its moisture. Then it comes over here to the leeward side, and it kind of sinks, okay? It heats up, and it compresses. So it does the exact opposite on this side than what's going on over here, okay? As a Regents question, it may appear something like this. A strong west wind steadily blew over Lake Ontario, picking up moisture. As this moist air flowed over the Tug Hill Plateau, the plateau received a 36-inch snowfall. The snow fell from the clouds that formed when rising air was what? Well, rising air, when it cools, it expands, and it condenses. Okay? So once again, we're looking for choice number 1. Okay? Orographic lifting. 56, porosity does not depend upon particle size, okay? you have, once again, two identical containers filled with, loosely packed sediments, but they're composed of the same material, but different sizes. Now, it looks like there's big spaces in between the big sediments and small spaces in between the small sediments. But if you were to add up the total amount of open space here in this container as compared to this container, it would be equal. In other words, there's not a lot of big open spaces, but there are a lot of little open spaces. You add up all these little open spaces, it's going to equal to the same amount of open space in this container here. So the graph you kind of need to know is as particle size increases, porosity remains the same. Okay. The diagram below represents two identical containers filled with the samples of loosely packed sediments. The sediments are composed of the same material but different particle size. Which property is most nearly the same for the two? Porosity, or choice A. Number 57, as particle size increases, permeability increases. So as the particles get bigger, that means they have bigger spaces. If they have bigger spaces, then more water can kind of go through them. Permeability, the ability of water to kind of infiltrate through. Okay, so as particle size increases, your permeability is going to increase. All right, which graph best represents the relationship between particle size and the rate at which water infiltrates permeable soil? A direct relationship. As one increases, the other increases. Or choice 4. Number 58. Capillarity increases when particle size decreases. Okay, capillarity is the upward movement of water through soil. Okay, it's against gravity. Basically, the tighter the space, the more capillarity you're going to have. Of course, water has these cool adhesive and cohesive properties. It likes to attach on to things around it. So the tighter the space, the more it's going to move up. All right. So the smaller the particles, the more capillarity you're going to have. Okay. Kind of like this diagram showing you here, the more narrow the space, the higher the water's going, kind of in a drinking straw, for example. Okay, you have a coffee straw versus a regular drinking straw. The water level in the coffee straw is going to be higher than the regular drinking straw. Okay. As a Regents question, soil composed of which particle size usually has the greatest capillarity? The smallest one there. Use your reference tables if you have to. Okay. But once again, we're talking about the smallest one there, which would be silt, or choice 1. 59. Potential evapotranspiration. That's a big word. It depends upon temperature. Once again, evapotranspiration. It's just kind of the combination of evaporation, okay, and transpiration. Once again, transpiration is plants releasing water into the atmosphere, okay. And evaporation, you know that obviously it's water going to the atmosphere from the oceans or lakes, okay. And the higher the temperature, the more you're going to have, okay. So it's just showing you, this graph of being a lot higher in June and July because it's a lot warmer in June and July. So you have a higher potential for that to occur. An area with a high potential for evapotranspiration has little actual evapotranspiration and precipitation. The climate for this area is best described as what? Okay, so once again, that means there's really not a lot going on. So it's going to be a little hot and arid. Okay, hot and arid because there's plenty of room in the air for it to go to. Okay. Number 60, water bodies moderate temperature. Okay, so what the graph is trying to show you here is an area in New York with the blue line and an area in Kansas with the yellow line, and it's kind of showing you the extremes. So in other words, if the town is by water, you're going to have more moderate seasons. In other words, your winters aren't going to be as cold and your summers aren't going to be as hot. All right. If you're inland away from the water, you're going to have more extremes. You're going to have really cold winters and really warm summers. Okay. So once again, water moderates temperature due to its high specific heat. All right. If you're going to see this as a question, compared to an inland location, a location on an ocean shore at the same elevation and latitude is likely to have what? Okay. So once again, it's going to moderate the temperature. So it's going to have warmer winters and cooler summers, or choice 3. Okay, that takes us through 51 through 60. Thanks for watching and stay tuned for our next video.